So learning to count, something that we all had to do once. And that's actually an interesting part of this. Those of you who haven't encountered different base representations before, it can be a little tricky at first, particularly once we start looking at representations where the base is greater than 10. But it's something that I think 6 or 7 year old you might not have had too much of an issue with. It's just the fact that certain things that we do when we represent or interpret a number, say in base 10, we once had to think about them when we were learning all this, 20 years ago or less for you guys, now it's just sort of become second nature. So it's something that a 6 or 7 year old you might have found relatively easy, but you just may not have thought about numbers in this way for a while. So a decimal system, this is the one we're all familiar with, is base 10. So base 10, what this means is we have 10 different symbols. So we've got the standard symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when we have a number in base 10, we have those symbols. And so we count in base 10. We can just, for the first 10 digits, just use those numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, let's say we want to write down 10 in base 10. So what we do is we've run out of symbols. We've reached 9, which is the symbol we use for the highest number in our base 10 system. So what we do is we sort of loop over. So that 9, we take that back to the lowest symbol, and then to the left of that, we increase that symbol by 1. So if there's no symbol there, we put a 1 down. If there is a symbol there, we just increase that number. So once we get to a 9, we would flip that 9 to a 0 and then write a 1 to the left of it. I guess you can see the pointer. Write a 1 to the left of it, so that's 10. And then we start again. 11, 12, 13, we just start incrementing that right number. So essentially what's happening here is that in a base 10 representation, the nth column, so if you're moving from the right, the nth column is essentially the number of the base to the n. So on the right here, and I'll show an explicit example of this, you don't have to keep track of all of this in your head. So on the right, this is the number of 10 to the 0, then 10 to the 1, 10 to the 2, 10 to the 3, so the number of zeros, number of ones, number of tens, number of hundreds, number of thousands, and so on as you move to the left. So this also is something that does come up, and when we get to JavaScript, you'll encounter this. So in computer science, we typically index things we start at 0. So when I'm talking about the nth column from the right, I don't start at 1, I start at 0. So it's not column 1, column 2, column 3, column 4, or position 1, position 2, position 3, position 4. It's position 0, position 1, position 2. So you can think there as position is more of an offset. So number of places away from the furthest, or from the starting position. This will trip a few people up later in the course. Not so much, I think different base representations and base conversions aren't too challenging. When we get to JavaScript and you encounter things like arrays, indexing there always starts at 0, but that's a few weeks away. So essentially also the leftmost digit is the sort of heaviest weight. So let's say you've got the number 429. That's 4 hundreds, 2 tens, 9 ones. The leftmost digit is sort of the biggest. So the leftmost, you've got the number of hundreds, then the number of tens, then the number of ones. So as you move further and further to the left, as you add more digits to the left, the number gets bigger and bigger, and you're using larger powers of your base. Binary system is base 2. So what we have here is we have, instead of 10 different symbols, 0 through 9, we just have 2, 0 and 1. So we count, though, much the same as we do with decimal. We start with the lowest digit, 0. We want to increase it by 1, move to the next symbol. So we have 1. Then we want to go to the next, so we have 2. Well, we're in a base 2 system, so we don't have a symbol for 2. So what we have to do is cycle our rightmost digit, so that 1 goes back to a 0, and then we add a new digit to the left, so we get 1, 0. So that is the number for 2. And some of you might have seen it's a fairly reasonably popular t-shirt. There are 10 types of people in the world, those who understand binary and those who don't. That's because the binary representation for 2 is 10, 1, 0. So now the base, however, is, so the value of each column, so if you think about the decimal moving from the right to left, it's the number of ones, tens, hundreds, thousands. Well, in decimal, it's, in binary, it's powers of 2. So the rightmost is 2 to the 0, 2 to the 1, then 2 to the 2, 2 to the 3. So that, as we move from start from the rightmost column, number of ones, as we move to the left, we have the number of 2s, 4s, 8s, 16s, 32s, and so on. However, essentially it's the same. It's just that the number of symbols that we're using and the value of each column is different. And you can see, you can have arbitrary bases, really. As long as you have sufficient number of symbols, you can have an arbitrary base. So you could have base 8, base 16. Both of those are fairly common and quite useful. You could have silly bases, base 13, base 72. If you want to, you could talk about even things like, say, base pi, if you really wanted to. That becomes a bit hard to represent because the values that you put in each column are no longer, you're not going to be able to have a finite number of symbols. But different bases, depending on you, so in computer science, bases 2, 8, 16, and 10, just because that's what we're all used to, things you will encounter. Different, say doing maths, you might encounter other ones. Just sometimes it becomes convenient to work in one base over another. And that's when, later in the lecture, when I start talking about the way in which computers represent data and different encodings, that's when you might start to see just exactly why binary is useful, and particularly when you're dealing with computers and computer science and the way data is represented by computers. So this is an example of binary and decimals. So we've got the first 10 digits or first 11 numbers, if you count 0 as a number, on the right here in the decimal system. So we start with 0, and as we increase the number, we move down a row. We increase our symbol. We just move to the next symbol every time. So 0, then next symbol 1, 2, 3, 4. So we get to 9. We run out of symbols, move to the next, so just cycle again to 0, but now we have to push a 1 to the left of that symbol, so to the left of that column, so that's a 10. Well, binary is pretty much the same. So we start with a 0, move to the next symbol, great, 1, now we want a 2. 2, we can't do that because we don't have a 2, no such thing as 2, so we cycle that digit and push a 1 to the left of that. Now, we want to increase, so we can just cycle a left digit. 11, great, that's our representation for 3. We want to increase that, we cycle a left digit, and now this one, we would cycle the digit to the left of that. We can't do that because that would go to 2. So again, we just cycle a digit to the left. So this is the same as moving from, say, 99 to 100. We would go to cycle the number of ones. That goes back to 0. We then would attempt to cycle the number to the left of that because we've pushed the number back to 0. So cycle the 9, that goes back to 0, and then we just have to put something in the new column. So you can see here that this pattern just continues. And if you want to interpret a binary number, you can just look at the value of each column. So this number here, we've got 100. Let's get a pen and highlight that. 100, so that's 1, 4, 0, 2s, and 0, 1s. So 0, 1, 0, 2, 1, 4. Compare that to 4 in the decimal system. It's just 4 1s. So we can have a look at, let's have a look at a larger number down the bottom, so where we actually have to use multiple decimal digits. So we've got 1, 10, and 0, 1s. So that's 10. In binary, 1, 8, 1, 2. So we have 1, 8, we have 1, 2, we have no 4s, no 1s. So you can see binary and decimals, they represent the same data. The expressive power of base 2 is exactly the same as the expressive power of base 4. It's just that we're using a different base. We have a different number of symbols, and therefore the meaning, the value of each column is different. So just as a little aside, odd and even numbers. So something that's nice about binary, and when you are practicing converting between decimal and binary, or indeed hexadecimal and binary, this can be a nice little property. Can someone tell me in the room, so I've underlined there the odd numbers, so 1, 3, 5, 7, 9, and I've left ununderlined the even numbers. We'll assume for the sake of argument we're going to call 0 even. Can anyone pick what is a common feature of all of the odd numbers there?
First digits.
Yes. So the least value digit for any odd number is 1, and the least value digit for any even number is 0. So this we can use this to perform, I suppose, just like a little sanity check. Let's say you've got the number 429 and you convert it to binary. You've been asked to do that in a quiz or an exam, say, and you want to do a quick little sanity check to see that you're right. You can have a look at that last bit. We know 429 is an odd number, so now we have a look at our binary representation that we've managed to get out, and we say, is it that last bit 1? If that last bit's 0, you know something's gone wrong, because 429 is an odd number. That's the lowest value bit must be a 1 because it's an odd. It's odd. So you can use that just as a quick little sanity check. Of course, if you may still have an error, you might have made an error somewhere else, but it's just a nice little way to very quickly check or see at a glance that something horrible hasn't happened. If you have an odd number and you wind up with a 0 as the least value digit, you know something's wrong. If you're trying to convert an even number and your least value digit is a 1, then you know something's gone wrong. So you can use that to see at a glance whether or not you've made a mistake. So converting between decimal and binary, so that's the next thing we'll cover. So there are a number of different ways to do this. Personally, I find this the easiest, at least with decimal to binary, is to find, you have your decimal number, find the largest power of 2 that fits into your decimal number. So you can write out from right to left the powers of 2, so 1, 2, 4, 8, 16, 32, gets very big very quickly. And find the largest power of 2 that fits into your decimal number, put a 1 underneath that, subtract that power of 2 from your decimal number, so you get the remainder, and then just continue to just repeat that process until your remainder is 0. So let's show an example of that. So let's convert the number 45. So we've got our decimal 45, we want to know what that is in binary. So we've got here the powers of 2 from right to left, 2 to the 0, 1, 2, 3, so 1, 2, 4 through to 128. We've just got the first 8 powers of 2. So let's find the largest power of 2 that fits into our decimal number. So 128 and 64 do not, but 32 does. So what we'll do is we'll put just a check mark above 32. And so now what we want to do is we want to subtract that power of 2 from our decimal number, from 45. So we get 13. Our remainder is 13. So now we just continue to convert 13. So does 16 fit into 32? It does not. Does 8 fit into, sorry, I said into 32. Does 16 fit into 13? It does not. Does 8 fit into 13? It does. So 8 fits into 13 once, which leaves us with the remainder 5. 4 fits into 5. Remainder 1. 2 does not fit into 1. but 1 does with a remainder 0. So now what we do is for every column where we had a check mark, so for where that power of 2 fit into our decimal number, we put a 1, and for every column where it didn't, we put a 0. And you can see here that that's our answer, 1, 0, 1, 1, 0, 1. So the answer I put up there has 2 leading zeros. You can do that if you like, much the same way that, I keep saying 429, but much the same way you could represent 429 as 00429. It's not incorrect, it's just redundant. By convention, I'm sure you're all used to this, you just start writing from the most significant digit, most significant non-zero digit. So you do the same with binary. Just start from the first one. If you put zeros at the front of it, so if you pad your string out with zeros, that's not wrong, it's just a little redundant. So you only have to start from the leftmost non-zero digit. You don't have to put the leading zeros. It can be useful to write out those zeros, just as a little aside, when we start converting hexadecimal to binary. There's a really neat little trick you can use that takes advantage of the fact that the base 16, so hexadecimal, is a power of 2. But anyway, that's a few slides ahead. So how about 27? So 27, we'll clear that. So 27, 16 fits into 27, 32 doesn't, so that leaves us with a remainder 11. 8 fits into 11 once, leaves us with a remainder 3. 4 does not fit into 3. 2 does fit into 3, and 1 fits into 1. So you can see I've sort of gone through that there. So much the same, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1. Binary to decimal is straightforward. This is the easiest of the lot, personally. So binary to decimal, we recall that the way base 2 works is it's wherever you have a 1, you are saying, let's say you have the number 101. So that first one is the number of 4s, the next is the number of 2s, the next is the number of 1s. So we're saying that's 1 4, no 2s, 1 1. So we can just sum. We can just say our 1 4, 1 times 4 is 4, plus no 2s, nothing, plus 1 times 1, so our 1 lot of 1. So we just, 101 is 5. So let's, as an example, we've got this binary string here. So 0, 1, 0, 0, 1, 0, 0, 1. So what we can say here is that this 1 here is the number of 64. So we've got 164, 1 8, 1 1. And we've got zeros everywhere else, so we don't worry about those columns. So that's 64 plus 8 plus 1. So we wind up with 73. So as a second binary string, so we can sum that one, that's 1 128. Another 8, and a 2 this time. So that's 8 plus 2 is 10, 10 plus 128 is 138. So that's binary to decimal is fairly straightforward. And you'll get some chances to play around and practice this in the lab. But let's finally, before I move on from this, let's talk about addition in binary. So we can add numbers in decimal. I think everyone here should be comfortable with that. But to add numbers in binary, it's really much the same. In the same way that when you add two numbers in decimal, you start from your least significant digits. You add them together. If that takes you above 10, or to 10 or above, so past the number of symbols that we have, we just roll over, so we keep counting, but then increment to the left, and then we just sort of carry to the left. So we can do the same sort of thing for binary, for adding binary numbers. So we add from the least significant, we add 1 plus 0, great, not a problem. 1 plus 0, great, not a problem. 1 plus 1. So we add those together and we get a 2. Well, we can't write 2, so we put down a 0 and just increment to the left, so carry to the left. And you can see here, so yeah, for those two, then yeah, as we get 2, we have to carry to the left, and then we just continue on. So there's zeros, we're fine. 1 and 0 is 1, 1 and 0 is 1. And much like decimal, if we had to, so we carry the 1 to here. Let's say we had a 1 there. So let's say instead of a 0, that was a 1. So now we would be adding 0, 1, and our carry. So in that case, that would become a 0, and that would become a 1. So essentially, we're just, whenever we go above the number of symbols that we have, we just roll over and carry something to the left. So the next time we perform our addition, we just have an additional carry that we have to add. So the algorithm, or the approach that you're using to add numbers here, is exactly what you learned when you were in primary school and you were learning to add 2 numbers. It's just the number of symbols that we have is smaller. Our base is different. It's the exact same process otherwise. So I'll go through this quickly, but things you can do with binary strings is you can shift them to the left and right. So let's say you've got this binary string here, the binary string for the number 2, and I'll pad it out with 8 zeros. Let's say we've got a full byte's worth of characters. So the number 2, so if we shift it left, we can do what's known as a left shift, which is where we take every digit and move it 1 to the left. So essentially, add a 0 to the end of our binary string. So what's happening here, well, what happens when you take a decimal string and you shift it to the left? So we've got 429. Let's add a 0 to the end of that. What happens then? What is the effect of shifting a decimal string to the left by 1?
Multiply it by 10.
Yes, you multiply it by 10. Binary is pretty much the same, except now you're multiplying by 2. Let's say you've got the string 1, 1, 1. So, and we shift this to the left. So this string here, 1, 1, 1, is the number of 2s, number 8's, number 32. So sorry, 1, 0, 1, 0, 1, 0, is 1, 2, 1, 8, 1, 32. If we shift that to the left, that becomes, this 32 becomes 164. So that's doubling the value of this one. So that one doubles in value. This one here, so 1, 8, it now becomes 116. So instead of 1, 8, we've multiplied the value of what that 1 represents by 2, and much the same for the 1 in this column. So what we're doing, if we left shift a binary string, we're multiplying it by 2, and this generalizes. For any base, left shift, you're multiplying by the base. So you can see here we've got the string 1, 0, which is 2, and we've left shifted it twice, and you can see that it's multiplying by the base, or by 2 every time. So to left shift is to multiply by 2, or by the base. Shifting right, much the same. What happens when you divide a decimal number by 10? When you right shift, sorry, I just said it, you divide it by 10. Well, same sort of thing. Shift right, divide by 10. So let's take our binary representation for 8. Right shift 4. Right shift 2. We divide as we shift right. So hexadecimal. Hexadecimal, we have here a binary string. So hexadecimal is base 16. We've seen base 2, we've seen base 10. You should all be familiar with base 10. Base 16 is another base that comes up a lot in computer science. One of the reasons you see it actually, and I mentioned earlier that 16 is a power of 2, that means that each individual hexadecimal character actually maps to 4 binary digits. So you can actually use hexadecimal as a really nice, concise representation for binary data. So say a really long string of 1s and 0s might be a little hard to read, but is less so when you represent it in hexadecimal, but more on that later. So we've got here a hexadecimal string, our binary string, and our powers of 2. So each column is just the number of 2s. Well, hexadecimal instead of columns from the right being 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, or 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, we use 16. So this is the 45 in binary. So hexadecimal, as we move from the right to the left, we have the number of 16s. So 16 to the 0, 16 to the 1, 16 to the 2, 16 to the 3. So as you move from right to left, the number of zeros, number of ones, number of 16s, number of 256s, and so on. So let's convert this 45 in, so I think it's easiest to learn by example. Let's convert this 45 to a hexadecimal digit. So what we're going to notice is that hexadecimal, if you were to write this down, it's actually, you have 2 16s, so 32 plus 13 ones. So we could write 213. So if I change this to the number of 16s to the 1 and 16 to the 0, and so that's the number of 16s and the number of 1s. What we actually have is we have 2 16s, so that's 2 times 16 is 32, plus 12, sorry. 13. Plus 13. So 2 16s is 32, plus 13 is 45. So we could write down 213 and be done with it, but this is problematic. We have 3 symbols. How do we parse this? Is this 2 256s, 1 16 and 3 1s? Is it 21 16s and 3 1s? We don't know. Oh, well, we know it's not that last one because we're in base 16, but yeah, it's ambiguous. So what we need is we need some symbols to represent the values that we have between 10 and 15. So when we're looking at a base smaller than 10, that's very convenient, at least in terms of the symbols that we've got, and it's possibly a little more intuitive because we can just use the same numbers that we're all familiar with, the same base 10, 0 through 9 symbols that we're used to. However, once we start dealing with bases that are larger than 10, we have to expand our vocabulary. So in this case, we use alphabetic characters. So 10 is instead represented by an A, 11 by a B, 12 by a C. So we can actually convert between hexadecimal and binary in the exact same way. We're coming up to the end of this. Just let me finish this slide, then I'm actually moving on to the representation stuff. So I can do that at the start of the next lecture. As I said at the start of this, that's sort of more motivating examples. So this is, just let me get through this slide. This is important. So what we can do is, whereas with binary, we converted between decimal and binary by finding the largest power of 2 that fit into our decimal number, and then writing down the number of times that fit, and getting a remainder, and then moving on to just with the remainder. We can do the same with hexadecimal. So we can say that this is the number of 256s, or the number of 16s squared. So 256 does not fit into 45, but 16 does, and 16 fits twice. So we write down that our 16 fit twice, and then subtract our 2 16s from our decimal number. So we subtract 32, and we get 13. Finally, 1 fits into 13 times, but now, because we need different symbols, what we do is we have a look at this table that I've got up the top here, and you can use this while you're practicing. Eventually, you'll just sort of internalize it. But you can see here that 13 is represented with a D. So that becomes 2D. So 45 in hexadecimal is 2D. A nice trick that you can use, however, if you want to convert, so that I converted there from decimal to hexadecimal. If you have binary, you can use that as a really convenient intermediate format for converting to hexadecimal. So let's say you can't, or you don't want to convert directly from decimal to hex. You could convert first to binary and then from binary to hexadecimal. And the way you do this is you take advantage of the fact that, as I said, there are 16 different combinations for every set of 4 binary digits. So 4 binary digits go up to 15. So 18, 14, 12, 11 is 15. So what you can do is you take your binary string and you divide it up into lots of 4. And you have to start, by the way, counting from the right here. Let's say you've got your binary string, so I'll put this up top, 101101. If you're going to partition this into groups of 4, you have to start counting from the right. Can't count from the left. So if I partition there, that's good. If I partition there, that's bad. So what you need to do is you may need to pad your string out with some zeros on the left to take it up to so you have a multiple of 4. The number of digits you have is a multiple of 4. You divide it into 2, and then you can just treat each of these segmentations like they're a separate number. So we can see here that we've got the number 1101, so that's 181411 is 13. We'll have a look on this table. 13 is a D. Now let's forget that even existed and just look at this new number. So instead of 128, that's going to be the number of 8s, the number of 4s, the number of 2s, and the number of 1s. We've got 1, 2, no 4s, no 8s, no 1s, 2. So we can actually convert directly. So convert groups of 4 binary digits directly. So that's why binary can be quite a nice intermediate format for converting between hexadecimal and binary. And actually, if you want to go the other way, so hexadecimal to binary, you can do the same thing. For every character, just find the 4 binary digits that correspond to that character and just substitute. So this is why you'll see, let's say you need to look at the raw data for a file and you need to actually see the raw ones and zeros. It's often more convenient to look at it in terms of the hexadecimal representation because you're dividing the total number of characters by 4 and it can be much nicer and much more concise way to see your data. Okay, so